We are going to have another example of the one sample t-test, the test that we use when we want to compare a sample mean with a population that has a known mean but an unknown standard deviation. Here is the problem. A coach was interested in whether high school males who had just watched a football game, scores below, had higher levels of aggression than high school males in general. Mu, or the population mean for high school males in general, is 14.3. We're instructed to use alpha equals 0.05 as our significance level. We begin as we have done before by parsing the problem. And I have laid it out for us. And so we will fill this in right here. So step one, we're going to figure out what our situation is. Population one, it appears, is these high school males who had just watched a football game. This is the group that is different from the population in general, in this case, because they had just finished watching a football game. And so we should be able to just type this in here and save a little time. High school males who just watched a football game. And population two is high school males in general. Move that over a little bit. High school males in general. What are we measuring or comparing between these two groups? We're going to be measuring levels of aggression. The tails refers to whether the researcher hypothesizes that the aggression will be higher, lower, or just different than the males in general. In this case, we can see the researcher thinks higher levels of aggression. If the researcher hypothesizes a direction in this way, that means that it's a one-tailed test and high. And of course, that means that the researcher is in this situation expecting that the sample will have scores lying only in this tail of the distribution, that their aggression will be higher than the population in general. So we're looking for a sample value, a sample standardized score or t-score that will fall in this range. We're looking for the sample to be in the shaded area. And if that happens, that means that we will have a significant difference in these two groups. So one tail high, the research hypothesis, we're simply going to state in terms of symbols at this point. We're just going to state that the mean for population one, those football players those males who just watch a game, will be higher than the mean for those high school males in general. The null hypothesis is the reverse of this. The mean for population one will not be higher than the mean for population two, or we could say the mean for population one will be equal to the mean for population two. And of course, when we say equal, we just mean that that score would fall somewhere in this white non-shaded area of the distribution. And when we say equal, that's what we mean, that it's not significantly different. So now we're ready to continue on to step two. And in step two, we are describing the comparison distribution. So step two. And in this case, just as before, we are looking at three pieces of information plus a drawing. We're looking at the center of the distribution. We're looking at the shape of the distribution, and we're looking at the spread. The center will simply be represented in the mu, the mean for the population, and that mean was stated in the problem. Mu equals, let's go back to that problem and find out. We can see mu equals 14.3. So we can fill this in here. I'm going to write it in blue, so it's maybe purple, so it's easier for us to see. 14.3. The shape, we're not going to be using the z distribution anymore. We're going to use the t distribution. And that is very similar to that z distribution, except the shape changes. The tails get fatter depending on the degrees of freedom or the number in the sample -1. And so in this case, we are just looking for t distribution with degrees of freedom equals n-1 equals, in this sample, we have 5 scores, 1, 2, 3, 4, 5, for each of those different males that were tested, and 5 minus 1 equals 4. So that's the distribution we're going to use. We're going to have to look up the value for that. And for the spread, we're just looking for the estimated standard deviation for the distribution of means. And so let's go ahead and get those calculations. To get the calculations, I sometimes find it easiest to write down first the basic information that we get from the problem. Remember, step 2 is the big fat step in this work. So the basic info would be things like n, the number in the sample, degrees of freedom, mu, the population mean, the sum of all the values, which we can use then to calculate the sample mean, or m. We have 2 means here. It's important to keep them distinct. We have the population mean indicated by mu and the sample mean indicated by m. In the end, these are the 2 values that we are going to be comparing. We're looking at, is this sample mean different from the population mean? Let's fill in what we know. N we know equals 5. Degrees of freedom we know equals 4. The population mean, we were told, and we wrote it earlier, is 14.3. The sum of these values that we need in order to get the, in order to figure out the mean, adding 18 plus 21 plus 25 plus 14 plus 17, we get a sum of 95. And in order to get the mean, we have to take the sum of all the scores, divide by n, which in this case, the sum is 95, equals 95 divided by 5, which equals 19. So the mean is 19. So we're going to basically be comparing this 19 with 14.3. Our next step then is to calculate the estimate the variance for this, estimate the variance from this sample to infer to the population. And so we're going to, I'll write this step down here. Next, we're going to estimate variance. And because we're estimating, we don't write it anymore as sigma, nor do we write it anymore as standard deviation. We're estimating, so now it's just s squared. It is neither of these two because we're estimating. So we're estimating s squared. The way we estimate s squared is we start by getting the sum of squares. And the sum of squares is the sum of squared deviations. So we're actually going to do this up above. I find this to be the easiest way because I'm so familiar with Excel. So what I generally do is I take and I write the mean. That is the sample mean, you'll notice, in this column. And then I figure out the deviations in the next column. So here I'm going to make a nice column for the mean. And then I make a column for x minus m, which is the deviations. Then I make a column for the deviations squared. and that will allow us to calculate the sum of squared deviations. So I'll write the mean in for each of these. The sample mean, I'm very careful to write the sample mean, will be, I'm going to just draw one more line here, will be 19. So I'll repeat it each time. 18 minus 19 is -1. 21 minus 19 is 2. 25 minus 19 is 6. 14 minus 19 is -5. 17 minus 19 is -2. And this was a -1, a little bit messy there. Now we have to square those. And when we square -1, we get 1. Square 2, we get 4. Square 6, we get 36. Square -5, we get 25. Square -2, we get 4. And in case you've forgotten what we're doing here, all we're taking is each value in this column right here and multiplying it by itself. -2 times -2 is 4. -5 times -5 is 25. So that's what we've done here. These are our squared deviations, and SS means the sum of squared deviations. So if we add all of these up, we'll get the sum of squared deviations. 1 plus 4 plus 36 plus 25 plus 4 equals 70. Here is the one point where we need to estimate then. To get the sum, to get the variance, the estimated variance, we have to take the sum of squares and divide by degrees of freedom. And that equals 70 divided by n minus 1, which equals 4. And that means that our variance for our estimated variance for this is 17.5. Now we are all set with the variance, but this would be applicable to a population of n equals 1. We actually have n equals 5, so we can't use this. We have to calculate the distribution of means. So let's do that next. We're going to calculate, we're no longer estimating, we're not going to use degree of freedom anymore. We're going to calculate distribution of means using the same formula as we've done before, which in this case is just the variance divided by n, and then we take the square root. So the variance for the distribution of means equals the variance divided by n, which in this case equals 31. Well, I'll write it out. 17.5 divided by 4 equals 17.5 divided by 4, which equals 3.5. Then we don't want to stay with the variance. We actually need, look what we need here, the standard deviation for the distribution of means. So we actually need standard deviation for the distribution of means, which is just the square root of the variance for the distribution of means, which equals the square root of 3.5, which equals 1.870829. So that means that we can fill this last blank in, we can complete our drawing, and we're done with step 2. 1.870829, or for the sake of the drawing, we're just going to use 1.9. That's for our drawing. And what we've actually done here is we've calculated our distribution of means, which, as you know, would be a long skinny distribution. But because it's really hard to draw on that, I'm going to leave it displayed as a fat distribution, even though we know that really it would be a thinner distribution. So as far as our z-scores, we would have our 0 about here, and we would have our 1 about here, our 2 about here, our 3 about here, our -1, -2, -3. Not spaced that well, but it's a starting point. And the values that would be associated with that would be in the center, we'd put the population mean, 14.3. And then we would need to add 1.9. So that would be 16.2 on the one standard deviation. And coming on the other end, subtracting 1.9, that would be 12.4. So this is what our distribution will look like. We do have these values, they're pretty tight in there. And now we're ready to compare our two distributions. We're no longer comparing apples and apples, n equals 1 with n equals 5. We're now comparing n equals 5 with n equals 5. So that I'll write in here. Okay, so our next step then, we're almost through, is to determine the cutoff point. And we do this, it's going to be a little different, remember, here. So we're going to look at our t distribution for degrees of freedom, t distribution for degrees of freedom equals 4, using, we've already stated, 0.05 for the cutoff point and a one-tailed high. We'll go to our critical value calculator, which is right here, and we'll type in that information. So our p-value is 0.05 and our degrees of freedom is 4. So we can calculate right here, and we find that for a right-tailed, a one-tailed test right, our cutoff point is going to be 2.13. They say critical value, that means the same thing as cutoff point. There is no difference. One is just a little easier to understand. So let's put our cutoff point at our cutoff critical value. I'll put that so you can see it. Is 2.13. We can leave it positive because we know we're looking on the upper tail, and that would put this line specifically maybe right about here for the exact cutoff point. And we're going to see if we can find our sample up in this distribution. So we're done with step 3. We'll move along to step 4, which is calculate standard score, standardized score. In this case, that's the t-score. And we know the calculation for that. The sample t-score equals, and let's run that over here. We will calculate t-score. And the formula for that is t equals m, our sample mean, minus mu, our population mean, divided by the estimated standard deviation for the distribution of means. And that in turn will equal our sample mean was 19. Our population mean was 14.3 divided by this big long number, 1.87 ... I'm going to use that whole number for my calculation, but I'm not writing it here because I ran out of space. And if we do that calculation, we find out that equals 19 minus 14.3 is 4.7 divided by 1.870829. And that leaves us with a t-score of 2.51226, which I will write over here as 2.51. And now I can put this into our distribution. So where is that going to fall? So here is our cutoff point, 2.13, nice and dark here. Our individual score is 2.51, which would be a little further out towards the tail of the distribution. It would be right about here between 2 and 3. And so this is our sample score, our sample mean, I should say, our standardized mean, t-score, equals 2.51. This makes sense because we look at where our 14.3 is. Here's 16.2. Next, we would have 18.1, and our 19 score that we had for our sample would reasonably be right about here. So this all makes sense. Our final step is we make our decision. We can see here that our t-score is more extreme. Our t-score of 2.51 is more extreme or further into the tail than our cutoff point so we reject our null hypothesis. If we reject our null hypothesis, we essentially cross it off, and all we're left with is this. And so the research hypothesis is supported, and we can say we reject the null hypothesis. High school males who just watched football have higher aggression than high school males in general. And we would write our statistics, T, and then in parentheses, the degrees of freedom, 4 equals 2.51. And then we write the probability of getting that, and we just say the probability of getting that score by chance is less than 0.05, less than 5%. And that is the end of our problem.